Greetings, Chem 2 students. Mr. Keister here with you again today. This is the video for Tuesday, November 17th, 2020, which is our scheduled 62nd day of school for the fall semester. Always keep in mind, though, the dates could change for a variety of reasons, but the lessons and the order that those lessons are presented will remain the same regardless. So let's take a look at our do-nows and see what our schedule is for today. We are beginning Unit 5 today. So you are picking up a new calendar. This is actually for Unit 5 and 6. Unit 5 is quite short. I'll discuss that in a minute. We got a Unit 5 notes packet and also our first assignment over Unit 5 over organic compounds. So those are pages 81, 82, and 83 respectively. There was nothing from yesterday as we had an exam yesterday. And in fact, Unit 4.2 exam is already graded and in the grade book in PowerSchool. The average in all three classes was in the low 80s, which overall is not too bad. Keep in mind, this is important, that for most of the units we have coming up, the rest of this semester after this one, and a lot of them in the second semester, keep in mind that nomenclature and formula writing is absolutely essential, all right? You have to know it. You have to. For those of you who struggled on this exam, you're going to have to get nomenclature and formula writing memorized. There's just no two ways around it, or it will haunt you again and again and again. I will return your exams hopefully tomorrow or the next day once everyone has taken it. So today we're going to be beginning a short version of Unit 5, which involves the nomenclature or naming and formula writing of common organic compounds. Today we'll start with the basic hydrocarbons. We're just going to cover alkanes today. We'll get to alkenes and alkynes and move on from there tomorrow. We'll continue on tomorrow through Friday, possibly Monday, and get as far as we can. Hopefully we'll get it finished up by Friday. If not, we will definitely have it finished up by Monday. You'll have an assignment over this that is due at the beginning of class tomorrow. And let me take a quick look at that. I believe it's going to end up that we're going to be doing just numbers 1 and 2 only for tomorrow. So not the entire assignment, but numbers 1 and 2 only. Okay? Okay, so included in this unit is the memorization of the basic prefixes and type of structures that you will see most often in organic compounds. And again, there will not be a separate exam for this mini unit, but this information will be on the next several exams and most definitely will be on the final. Okay, so having said all that, let's bring up the board and get to our lesson for today. All right, so let's first talk about the abundance and importance of carbon. All right, so the study of the compounds that contain carbon other than carbon dioxide and carbon monoxide gases. And the reason those two are not considered organic is because hydrogen must also be bonded to at least one carbon in a compound for it to be termed organic. All right. So the study of those compounds is called organic chemistry. So carbon is found in all living matter, all right, hence the name organic, and is present in body tissues, is a major component of most foods, and is found in fossil fuels, those composed of decayed, once living matter. Fossil fuels include coal, petroleum, natural gas, and wood. I think I said coil because oil is included in there, by the way. And so if you think about those ones, coal, oil, petroleum, oil is, of course, from crude. Petroleum is crude oil products. Natural gas and wood. Those are currently our main energy sources in this country. Now, we utilize some other sources too, some other alternative sources such as nuclear. We've talked about that. Oh, we use wind power. There's a lot of those windmills up around where I'm from. Hydroelectric power, of course, geothermal, and others. We utilize all those now to a much larger degree than we used to. But still, our number one energy source is by the burning of fossil fuels. Okay. So carbon is one of the few elements that in nature is found in its elemental form. And it actually occurs as 3 different allotropes, depending on the arrangement of its atoms. All right. Now, how can carbon in its elemental form, in other words, only carbon atoms involved, how can we have 3 different structures? Well, it depends on where and how and under what conditions those carbon atoms are connected together. Depends on the pressure involved, the temperature involved. And so basically, of course, carbon is found underneath the ground. And of course, depending on how deep you go and under what type of formation you're in down there, you can get different allotropes or different formations of carbon atoms that bond together, or they should say combine together in different ways. So let's talk about those real quick. So the first allotrope of carbon is called fullerenes. These are the blackish brown solids. They're part of the soot that forms when carbon-containing compounds are burned with limited oxygen in a combustion reaction. All right, so here we're talking about coal, basically, all right, and peat and those types of things. They look like spherical cages that resemble a soccer ball and are formed by 60 carbon atoms arranged in interconnected 5- and 6-member rings. Its actual name is Buckminster fullerene. That's a mouthful. Buckminster fullerene. But they're often called by a little nickname, and that is a buckyball. I'll show you what these all look like here in just a minute. Diamond is another allotrope of carbon. Diamond is the hardest material known on Earth. Its carbon atoms are arranged in a tetrahedral network with one another. That should ring a bell, tetrahedral. Since carbon has 4 valence electrons, that is a very common structure for carbon. A diamond is formed deep within the Earth under intense heat and pressure. And so that is the main factor involved there in the way that diamond is formed. Diamond has an extremely high melting point, about 3,500 degrees, and is an excellent conductor of heat. Of course, we also know it is actually quite precious. All right. Diamonds are a girl's best friend. If you haven't figured that out yet, everyone, you will soon enough. Never mind. The third allotrope of carbon is graphite. All right, graphite. We commonly call it pencil lead. All right. Keep in mind, though, that pencil lead is not lead at all. It is actually an allotrope of carbon, graphite. Graphite, its carbon atoms are arranged in layers that form thin hexagonal plates. The layers are fairly far apart from one another, and they're weakly held together. Remember, nonpolar covalent bonding leads to London dispersion forces there, and so with those intermolecular forces being pretty weak, as you well know, graphite or pencil lead can break off quite easily. And if you've ever noticed it, if you have a regular pencil, like a number 2 pencil, you will often find that one side of the pencil will break off, the writing part, the lead part, the graphite part will break off, and on the other side it remains whole. In other words, you can actually see it'll break off in a smooth straight line. That's the junction between plates there, what we're talking about here, those thin hexagonal plates. So this explains graphite's softness and ability to crumble easily. So let's take a look at those real quick before we come back to the lesson. So here are the allotropes of carbon. So here's fullerenes or buckyballs. As you can see, they are in interconnected 5- and 6-member rings. They certainly do look like a soccer ball. All right. Here's what we're just talking about, graphite, where we have these hexagonal plates. All right, these 6-member carbon rings is what they call them. And they're in layers. And as you can see, the layers are spread fairly far apart. Not a strong attractive force between those layers. And so again, graphite or pencil lead can crumble and shear off quite easily. And then diamond here is our structure that is extremely hard and much higher melting point. Again, the diamond is formed under intense heat and pressure. And so you can see the buildup of the tetrahedral network here. You can see each carbon atom has 4 carbon atoms associated with it, and then each successive carbon atom has 3 more associated with it for a total of 4, and so on and so on and so on. And it's a very, very hard substance. All right. So those are the 3 allotropes of carbon. Again, formed under in different conditions of temperature and pressure and so forth. All right. So let's get back to the lesson here. All right. Organic compound nomenclature. Organic compounds are named somewhat differently from all other chemical compounds, and the prefix used in the name indicates how many carbon atoms are in its basic structure. So keep in mind that carbon-containing compounds are going to be molecular compounds, all right? Covalent bonding, okay, because of carbon's electronegativity. And so we've learned nomenclature of molecular compounds. Remember, we used prefixes mono, di, tri, tetra, so on and so forth. All right. Well, in organic molecules, they have their own rules in regarding to nomenclature. I actually like them because no matter what type of organic molecule you're dealing with, there's a prefix in there that'll tell you right off how many carbon atoms are in it. Then, of course, you have to know the rest of the structure, but that's what we're going to learn here in the coming days. All right. So here are our prefixes, and honestly, I'm going to draw a line underneath the first 4 because these are really the only ones that are different, all right, from the ones we learned in our last unit over nomenclature of molecular compounds. In an organic molecule, the prefix for 1 is not mono, but instead it is meth, all right? So methane, methanol, things like that, terms like that tell you that there is 1 carbon atom in that compound. The prefix for 2 is not di, it is eth. So we have ethane, ethene, ethine, ethanol, ethanal, ethanoic acid. There's all kinds of them. And just the fact that all of those words begin with eth tells you that there are 2 carbon atoms in that particular molecule. The prefix for 3, rather than tri, is now prop. All right. I'm sure most of you have heard of propane. If you live out in the sticks like I do, a lot of us heat our homes with propane because we can't get natural gas lines out in the middle of nowhere. So if you see one of those big white tanks sitting in the back of somebody's yard, chances are that that's propane. Also, most of us have a barbecue grill, a gas grill, and those little tanks that we use for that we go to the store to get them refilled and whatnot, those are propane as well. And so propane means 3, all right, prop. There's also propene, propine, propanol, propanoic acid, propanal, and propanone, and there's a bunch of other ones. But all those contain 3 carbons. And the prefix for 4, rather than tetra, is now bute. Most lighters use butane, all right? And that is a 4-carbon compound. We also have butene and butanol, butanoic acid, and a host of others. You see the prefix bute in there anywhere, that means there's 4 carbons. Now, when you get to 5 and go on down through 10, they're essentially exactly the same as we learned in the nomenclature of general molecular compounds. Remember, 5 was penta. Okay, well, now we've dropped the A off of all of those. It's just pent. 6 is hex. Remember hexa. 7 is hept. 8 is oct. 9 is known. Remember nona. And 10 is dec or deca. All right. So, but again, in organic, we drop that A off the prefix. So 5 through 10 is pent, hex, hept, oct, known, and dec. I listed a couple of other ones here just because you might run across them sometime. 12 is dodec. I don't remember if you in math, but 12-sided figure was called a dodecagon. Same prefix. 20 is icos. All right, icos. So you don't need to know those two, but I just want to tell you what they were in case you run across them. But the first 10, definitely. All right, the first 10, you must know those prefixes. All right. All right, so let's get to, we're going to start with hydrocarbons today. All right, actually, just going to talk about one type of hydrocarbon. So organic compounds that contain only carbon and hydrogen, all right, only carbon and hydrogen, no other atom, are called hydrocarbons, all right, and they are grouped mainly by the type of bonding between the carbon atoms. So again, these are covalently bonded molecules. So basically, the type of bonding is, single covalent, double covalent, triple covalent, possibly a coordinate covalent. That's really all we're talking about here. So we're going to start with the first type of hydrocarbon, which is an alkane. Alkane. Ends in ane. All right. These are hydrocarbons that contain only single bonds. Only single covalent bonds between the carbon atoms. This type of hydrocarbon is called a saturated hydrocarbon because all the carbon atoms have 4 single bonds around them, and thus have the maximum number of hydrogen atoms bonded to them that they can possibly have. So I'm sure you probably heard of saturated fats. A fat is an organic molecule, by the way, and saturated fats have the maximum number of hydrogen atoms around all the carbon atoms that they can possibly have. All right, and so that's why they're called that way, or why they're called that. So alkanes have the general formula of C to the N, H to the 2N plus 2. So however many carbon atoms there are twice that number plus 2 hydrogen atoms, all right? So let's take a look at the 10 basic hydrocarbons, all right? So let me raise this up a little bit. All right, so I've got 3 columns here. First one is labeled its inorganic formula. Probably a better way to term that is its regular formula. In other words, the formula that we would use when we put one of these in a chemical equation. All right. Here's its name. And then over here on the right side is its organic formula. I'm going to show you those today, which is an organic formula is basically a shortcut version of a Lewis structure. All right. And so let's look at that. So the first one is methane. It's got a common name. We call it natural gas. So if your home is heated by natural gas, the school is here, our Bunsen burners have natural gas in them, all right, then that means that we are heating via the use of methane, all right. So methane, of course, just has 1 carbon. We've actually drawn it before. So if it has 1 carbon and it has all single bonds in it, like all alkanes do, then of course it has 4 hydrogens. Remember, it's tetrahedral, and so those hydrogens are bent a little bit, all right? And so its organic formula, basically for methane, is exactly the same as it would be as for its regular formula, and that is just CH4. So it's actually the same. So the regular formula and the organic formula for methane are the same. That's not true of the rest of them, all right? So let's look at the second one, ethane. All right, so ethane has 2 carbon atoms bonded by a single bond. So how many spots does that leave for hydrogen? Well, let's look. Each carbon has to have 4 bonds around it. So there we got 1, 2, 3 there, and 1, 2, 3 there. All right, so 6 hydrogens. So the regular formula for ethane is C2H6. But now our organic formula, we draw a little differently. And it's based off of this Lewis structure right here. These are all hydrogens, of course. I'll put them in there, but we're not going to put them all in there for all of these. So those are all hydrogens, all right? So now take a look at what I'm going to write here. So here's the organic formula for ethane. CH3 single CH3, all right? Now, do you see that this came from the Lewis structure? So the carbon on the left has 3 hydrogens attached to it, CH3. Carbon on the right has 3 hydrogens attached to it. That's another CH3. And then we draw the single bond between. Now, don't let that confuse you. We're not saying that this single bond is between this carbon and these 3 hydrogens. That's not true, and you can see that from the Lewis structure. That single bond means that the 2 carbons are bonded together via a single bond, okay, a single covalent bond. So this is the organic structure for ethane. This is its regular formula, all right, C2H6. That's the one you'd use when you put it in an equation. All right, so propane, C3H8. So again, now we have 3 C's, all right? So how many hydrogens will fit around the left carbon? Well, 3. We're just completing the octet rule. How about the middle one? Only 2 now, all right? Only 2. And then the far right one, again, 3 there. 3 there. So again, all of these are hydrogens. This is a hydrocarbon. All right, so we have C3H8. Well, look, we got 3, 4, 5, 6, 7, 8. C3H8, all right? And remember the general formula, C to the N, H to the 2N plus 2? All right, well, in propane, we had 3 carbons, so N is 3. 3 times 2 is 6, plus 2 is 8 hydrogen, which is exactly what we drew here in its Lewis structure. All right, so its organic formula would be CH3 single CH2 single CH3. Okay? After we do this next one, I think you'll see a pattern. All right? Butane has 4 carbons. 1, 2, 3, 4, all single bonds. So how many hydrogens can fit around each of those? Well, on the left one is 3, second one 2, third one 2, far right one 3. All right? I'm not going to draw all the hydrogens in now. We know what they are. So let's look here for butane. CH3 single CH2 single CH2 single CH3. All right? You see a pattern emerging here? Take a look at butane or propane and take a look at butane. What's different? As each alkane gets larger by 1 carbon atom, it also adds 2 hydrogen atoms. So basically, as we draw these chains for our organic formula, all we're doing is adding another CH2 in the middle. All right? So for pentane, which has 5 carbons, 3 hydrogens on the end, 2 in the middle, 2 in the middle, 2 in the middle, and 3 again on the far end. Same thing. CH3, CH2, 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 CH3. Okay? And a single bond there between all the carbons. All right? You kind of see how this is working out now? Hexane, C6H14, 6 carbons, 3 hydrogen, 2, 2, 2, 2, 3. CH3, CH2, 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 CH3. 1, 2, 3, 4, 5, 6. All right. And again, C6H4, 14. Well, 3, 5, 7, 9, 11, and 3 is 14. C to the N, H to the 2N plus 2. That's the general formula for all alkanes. All right. So let's finish this up here with the last 4. Let's go to the next page. Oh, I know one thing I forgot to write down. Back with C3H8, propane. I mentioned that we use that a lot to heat our homes. For those of us that have to use that but can't get natural gas, which is methane. And we all lot of us use it in our barbecue grills. All right. It also has a common name. As when you buy it, you may not buy it under the name propane. You might buy it under the name bottled gas or LP gas. All right, LP, which actually stands for liquid propane. All right, propane is actually a gas. We'll talk about that here in a little later. But when it's bottled under intense pressure and you get those gas particles pushed closer together, of course they will condense and liquefy, and in that tank, that propane is in the liquid form. If you notice though, if you open the valve at the top, and it comes shooting out of there, doesn't come out shooting out as a liquid, it comes shooting out as a gas. That's because when you expose that to a standard pressure, normal atmospheric pressure, it immediately vaporizes back into its normal phase, which is the gas phase. So C3H8 has a common name as well, bottled gas or LP gas. Okay, so let's get back to where we were now on the next page. C7H16, well, 7 carbons, the prefix is hept. This is an alkane, so it's called heptane. So we have 7 carbons. Again, 3 on the end and 2 hydrogens on all the C's in the middle and 3 on the far end. So CH3, and then I got 1, 2, 3, 4, 5 CH2s. 1, 2, 3, 4, 5, and then another CH3. Regular formula is C7H10, H7C16. Sorry. You can see why when we're writing an equation, we don't use the organic formula. Pretty long, all right? So that's why we use the short version or the inorganic or regular version in equation writing. So C8H18, octane. Okay, well, that's got a common name too. Octane is the main component of gasoline. Gasoline. All right, so when you buy gasoline, I don't know if you've noticed this, when you pump gas, you usually have 3 choices, 87, 89, and 91. You usually say that's regular grade, mid grade, and ultra grade or whatever they call it. Well, that number associated there, 87, 89, 91, that's the percentage of octane in that gasoline. So gasoline is not pure octane, although race cars use pure octane as their fuel. But a majority of gasoline that we purchase for normal vehicles is octane, and the rest is some other additives thrown in there, mainly ethanol now. So anyway, C8H18 octane is the main component of gasoline. So it has 8 carbons. 1, 2, 3, 4, 5, 6, 7, 8, as evidenced by its prefix, op. And again, 3 hydrogens on the ends, 2 on everything in between. Let's see, we have 3, 4, 5, 6 CH2. So we have CH3, CH2, 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 CH3. 3, 4, 5, 6, 7, 8. Wanted to make sure I didn't lose count there. All right. And then C9H20 would be no name. It's going to add another carbon. And 2 more hydrogens. CH3. Now I got 7 CH2. 2, 3, 4, 5, 6, 7. Man, I got to start writing smaller. Woo. Barely got it in there. All right. So there's a CH3, 7 CH2s, and then another CH3 on the end. And finally, our last one, decane. That's 10 carbons. There we go. Okay, last one. CH3. Now we got 8 CH2s in there. 1, 2, 3, 4, 5, 6, 7, 8 CH2s. 3. And that, my friends, is decking. All right, so let me take a quick look at that assignment again, because that's as far as we're going to go today. I just want to double check. And yes, we are just going to do numbers 1 and 2 only on this assignment. So just numbers 1 and 2. We'll hit the rest of it tomorrow and also get started on the next one as well. So I think that's it for today. All right, so we're getting started on organic nomenclature. All right, nomenclature of organic compounds. And remember those prefixes. All right, meth, eth, prop, bute, pent, hex, hep, oct, non, and dec, 1 through 10. We're going to be using those every day until we get through with this little mini unit. And again, those prefixes are important because they tell us how many carbon atoms are in that particular organic compound. So, till next time, this is Mr. Keister signing off. Stay safe, everyone. Take care. Keep working hard and stay focused. And I'll catch you next time. See ya.